Welcome everybody. We're going to move into the area of how X-rays are produced now. This is chapter 6, and interestingly, the instructions online say that you should only review the sections on Compton and photoelectric interactions. Well, they're not really listed in this particular chapter. They are in chapter 7. However, I believe that it's very important that you understand these interactions with the tube itself. So this chapter covers how X-rays are produced and some of the interactions that occur to create X-rays. And we need to cover that before chapter 7. So I'm going to cover the entire chapter, and this will also help you because you've got to have chapter 6 at a later date anyway, so you need to know all about this particular information, okay? So hang on, let's get going. As usual, these objectives come from the textbook. It looks like a lot, but you do actually need to know all this information. You need to know about the heat production in the X-ray tube. You need to know about characteristic photon production, Bremsstrahlung photon production, and then we need to determine the characteristic and Bremsstrahlung energy and how that energy is created. Then you need to know about inherent, added, and compensating filters, and then how beam quantity and how that means how much and what affects it, and then beam quality and what affects it. We're going to talk about half value layer, and then talk about the emission spectrums of X-ray. So we've talked about the electromagnetic spectrum. This is a little different. This is only X-ray. Then we're going to talk about the effects of the different factors that actually affect emission spectrum. You can read those, okay? But remember, you really need to know all of this information, and there's a lot of good tips that I'll be talking about that are in some tables as we go along. Now, as an introduction, I want you to know that this chapter examines the anode-target interactions. So the other interactions in chapter 7 are with the tissue of the person that you're actually X-raying. This is the anode-target interactions and how we actually produce X-ray at a micro level. It focuses on the interactions in the anode target that result in X-ray photons, as well as the properties, the characteristics, and the factors that influence the nature of the X-ray beam. There are several complex and overlapping processes that result in the radiographic image. You may have already heard people in the public who say, oh, you do nothing but push a button. Trust me, there's more to it than that. You actually need to understand how all of this works because you are applying radiation to the human body. The radiographer's actions at the control panel are the ones that directly determine the nature and the makeup of the X-ray beam. The nature and makeup of the beam, in conjunction with the patient, the image receptor, and the processing, determines image quality. So all that together is what determines if you have a good image or a bad image. And the X-ray machine is a tool in this process. Understanding this tool is one factor that determines the skill of the radiographer. That's our goal here. We're all going to become a radiographer when you are through at the end of 2 years. And all of these are affected by the patient's makeup. So the patient actually determines what technical factors that you use at the control panel. So then we'll cover that in the next chapter, but you have to understand what you choose and your actions in doing so are what makes the quality image or the quality of the image. And if that patient's thin or fat, I hate to use the word fat, but it's a fact, or if they have a disease process, all of that affects how we adjust our technique. Now we'll talk about those particular changes later on, but you need to understand why you actually choose the exposure factors that you choose. So this figure is the inside of the X-ray tube. We've seen that before, and if you look closely you can kind of see that oil that's floating around right in there. Once the technical factors have been selected, electricity travels to the anode, the cathode, and the filament, and electrons are boiled off at the filament. And that's what we call thermionic emission. Don't ever forget that word. Thermionic emission is the boiling off of electrons. And then they stream across to the anode at tremendous speeds, 1/2 the speed of light. The filament electrons penetrate the face of the target, and that's also called the focal track, at approximately 0.5 millimeters, interacting with the tungsten target atoms in their path. So that's how the target actually works. Now, I just mentioned the word electricity. We have another whole chapter. We'll talk about the electricity in the circuit that we use in all of our machines. But the main thing is knowing you select technical factors, that electricity goes, electrons are boiled off, and then they hit the anode target, and then that's what produces the X-rays that we use. So inside the tube right here, when we increase the kinetic energy of the incident electrons, we are also increasing quality and quantity, and then we increase the number of target interactions. So increasing the energy of the electrons means that we get more, and then we have more quality. Electrons undergo over 1,000 interactions to dissipate all of that excess energy. Those are the electrons coming off the tube, and then we increase the quantity, which means there's more electrons, and quality of the electrons, that's the energy. We'll talk about that in just a little bit. And this way we can increase the number of target interactions and produce more photons, but we also increase more heat that's generated in the tube. So all of this occurs within only 0.25 to 0.5 millimeters of the target surface. If you remember back to the last chapter, when you look at that rotating anode, it's not like it covers the entire anode. It's just one little piece of it. And so here is how the tube is made. So here's our glass envelope right here. This is a lead housing. There's our cathode sending these electrons, and when they do, there's our target, and it only hits a little bitty bit, but then when it comes out the window for the X-ray beam, it's a larger beam that comes out. So just understand again how all that works inside the tube. These filament electrons interact with target atoms to produce X-rays in two ways, and these are the two ways that we're going to talk about. One is characteristic, and one is Bremsstrahlung, and these are the two that you need to know. So when you see these two interactions, those are interactions at the X-ray anode or the X-ray target. You should also remember most of the interactions, that's 99%, do not result in X-rays but produce only heat. Keep in mind that there are thousands of interactions taking place inside the target, but for this sake of explanation, we're going to only focus on a single event. You can go back to chapter 2 if you want, and then look at the structure of the atom if you need to. But now we're going to talk about it as an interaction within the tube. So remember, when all of these electrons hit the target, 99% go to heat, 1% becomes an X-ray. And depending on the factors we choose, you're either going to have characteristic X-rays or Bremsstrahlung. Now right here, doesn't mean much, but by the end of this conversation, you'll know why the Bremsstrahlung looks like this and characteristics look like that. Okay. As filament electrons enter the anode target, most interact with the outer shell electrons of the tungsten atoms, and we already know about that. They do not transfer enough of their kinetic energy to ionize the atom, but rather just enough to raise them to a higher energy level. This excess energy is immediately given off as infrared radiation, or heat, as the outer shell electron returns to normal. There are thousands of interactions, and I've already talked about that, and in one single exposure, but 99% cause heat, and that's called infrared energy if you want to talk about it. But the end result is that most of the energy from the filament electrons is lost as heat, and only 1% results in X-ray production, which we've already kind of talked about, okay? So make sure that you understand that. So, you know me, I'm going to throw in a picture. So, characteristic X-rays are emitted when outer shell electrons fill a vacancy in the inner shell of an atom, releasing X-rays in a pattern that is characteristic to each element. So, that's why it's called characteristic. Characteristic X-rays were actually discovered by Charles Glover Barkla in 1909. He later won a Nobel Prize in Physics for the discovery. And the name characteristic comes from the fact that the binding energies for electrons in an atom are unique. That means characteristic for a specific element. Therefore, the difference in binding energy is also unique for the element in question. So that's where we get the name characteristic. The reason Charles here found these, it came afterwards. What you will find, and we'll get there after we talk about characteristic, but the Bremsstrahlings are the ones that are actual X-rays, okay? So, characteristic interactions involve the filament, and it's the filament electron and an orbital electron of a target atom. So we've already talked about how atoms join, how they change, how they move, but in general, a filament electron enters a target atom, strikes an orbital electron, and if its energy is greater than the binding energy of the orbital electron, it's removed from orbit. Just to say another way, so you kind of get an idea, an incoming electron strikes an orbital electron from a target, and its energy is greater than the binding shell of that orbital electron, it is knocked out. That's what makes the atom unstable. Then those vacancies are quickly filled by electrons that drop down from outer shells to fill the inner shell vacancies. And as it does this, it emits excess energy as a photon. The energy of the photon is the difference between the two shells. And there you go, the difference between the two shells. If it's a big drop, the photon has a high energy level, and that is what is an X-ray photon. So if you look at this right here, here's our incoming right here, and then it hits, strikes an orbital electron, so this is an orbital one, and if its energy is greater than the binding energy, then it knocks it from the shell, and then you have that projectile that sends out. Now, what you also heard me say here, and I'm going to go into the next one, is that it's called a characteristic cascade. So in Chapter 2, remember we talked about orbital shells that fill the shells nearest the nucleus outward, and then a vacancy in that shell makes it unstable. To correct it, an outer shell electron drops back in, so it falls, and that's what creates this characteristic cascade. So to do so, the outer shell electron must expend some of its energy, and that energy is given off as a characteristic X-ray photon. There's your picture from the book, so you can look at that if you would rather see it there. But note, when the first orbital electron drops to fill the vacancy, it moves, so it leaves another vacancy. That vacancy is then filled by another outer shell electron, giving up some of its energy, producing another characteristic photon. So that whole process of outer shells, and what you're seeing right here is what if you can see these little arrows, so here's your filament electron, and it hits here, knocks it out. Well, then this little bugger is going to go boop, and then this one falls into its place, then this one falls into its place, this one into its place, and then all the way out here, so everything just keeps falling in a cascade type reaction. Each time an orbital electron moves to a lower orbit, a characteristic photon is produced. So not only do you have that very first one that pops out right here, then this one, well, then it comes out over here, and then this one comes out over here. So there's always another characteristic coming out, but it's not going to where you wanted it to go. So if a filament electron removes a K shell, the most likely electron is going to be the L, and then when the L does, then it's the M that goes into it, so just know that it goes into order. And then note that the removal of the orbital electron establishes the environment for X-ray production, and it's the expending of energy during that cascade that produces characteristic X-rays. So If it were just the one, then, that would be a problem. So since it's not, we know that it is one right after the other. Characteristic photons are so called because their energy is characteristic, and that depends on the difference in binding energy between the shells involved. The electron shells of each element have a specific binding energy. We have a table on the next slide that presents binding energies that can be assumed for tungsten. Now, what you need to know here is that a tungsten atom has 74 electrons orbiting its nucleus in 6 different shells, and that's similar to what we're looking at right here. The filament electron may interact with any of them, but medical imaging or radiology focuses on the K-shell interaction because that's the highest energy and the most useful for imaging purposes. So again, that's why we use a tungsten target, because it interacts so well. And then here's the whole how it's made. It knocks one out, and then there's an X-ray that's involved. So here's the example. So remember from chapter 2, every orbital electron is held in orbit by binding energy. The closer to the orbit, so that K is the closest to the nucleus, then the stronger the bond. So the K shell in a tungsten has 69.5 kilo electron volts. And I'm sorry that V is missing right there, but it should be KeV for all of them. And then as it goes out, you notice how it drops. So that next shell is an L, and it drops to 12, 2. So you can see how it goes like that. For a filament electron to remove that electron, it has to have an energy equal to or greater than 69.5 kilo electron volts. So let's go back to this picture right here, if it wants to hit this K shell for a tungsten, what's coming in has to have at least the same amount as that K shell does. So it can go through all these and it's not going to bother it because we know it's higher, but these are the ones that drop down and fill it, and then when they fill that vacancy, then it kind of builds that energy back up. So for all practical purposes, using a general purpose X-ray machine, if a radiographer selects a KVP less than 70, then there are going to be no photons produced from the K-shell interaction because we use tungsten as the target, and it has to be at least this, so 69.5. And if you have less than that, it's not strong enough to knock that K-shell out. That's how this all works. And that's important for you to remember, because then when we talk about the beam quality and the quantity, it'll make sense to you. So the characteristic photon is named for the shell being filled in each case. Therefore, if an outer shell is filling a K shell, regardless of where it came from, now it's called a K characteristic. So that's the one that's shot out. And then if electron filling an L shell, then that resulting photon is called an L characteristic. And you can just go on and on. To find the energy of a characteristic photon, the radiographer needs to know the target element, and it's usually tungsten, and then the shells that are involved. Using this information, you can subtract the binding energy of the farther shell from that of the closer shell. And then the K-shell electron absorbs the kinetic energy from the filament electron and re-emits it as heat energy. And then this happens with any other orbital electron, regardless of shell, if the filament electron does not have sufficient energy to remove it. In that case, the filament electron loses its kinetic energy and it just drifts away. If, however, that same filament electron had 100 keV of energy, it would easily remove the K-shell and be deflected in a new direction, and it would still have 30 keV of energy left. Therefore, it can interact with another. So that's just how it kind of works. I'm sorry, those are just a lot of words, but as it moves and you name them, if it hits the K-shell, then that electron is bumped out, then that is a K characteristic photon. And then the L one, when it gets hit, it would be an L characteristic. So here's an example. So If characteristic interactions, they have characteristics. To remove an orbital electron, the filament electron must have kinetic energy equal to or greater than the binding energy. So let's pretend our filament threw us a 50 keV electron. And it interacts. So the filament has 50, and then it strikes tungsten, which has 69.5. Well, I just said the filament must have equal to or greater than the binding energy. So if the filament that comes and hits the target, and the K-shell has 69.5 because it's tungsten, that means there is no energy to remove it. All it's going to do is produce heat. Nothing gets bumped out of its orbital shell. So know that your filament has to be created. How do we create that filament? We use techniques, and we'll talk about that in just a second. So that's how characteristic radiation occurs at the target. Now let's talk about brimstalling. Brimstalling interactions is the other tube interaction that you need to know about, and we also call it brims. Sometimes, there it is at the very bottom. Sometimes we just say brims because brimstalling gets very long for too many words. Brimstalling is a German word that roughly means breaking or slowing down, and what it does is exactly what this interaction involves where the filament is concerned. So instead of stopping it, it breaks it and it slows down. And if this interaction, the filament electron misses all of the orbits and interacts with the nucleus. So on this one, you're not worried about it actually hitting any of the orbital electrons. It's going straight for the nucleus of the atom. So in layman's term, the nucleus is positive, the electrons are negative, and so there's a mutual attraction. But when the electron wants to get close to the force field around the nucleus, it slows down and changes direction, and then that makes it scoot away. Instead of throwing it out like a ping, it's just, oh, I'm going to get out the way here. So the loss of that kinetic energy appears as an X-ray photon. The electrons must have enough energy to break through the shells to get to the nucleus, but the force is too overpowering. So that's what brimstalling means. And Wilhelm Röntgen, however you want to say that, he discovered the X-ray in 1895, and he's the one that's credited for brimstalling interactions, because brimstalling interactions are the X-rays as we know them. When a fast electron interacts with matter, they may lose energy by Coulomb interactions, as well as a radiative process. Energy is mainly lost through repeated collisions with atomic electrons, which cause excitation and ionization. Then you have that electron-nuclear interaction, which abruptly changes the electron direction, and that happens most of the time. Classically speaking, the strong acceleration of that electron as it is deviated from its straight line path is what gives rise to radiation. Some of the electron's energy is lost, and that's because it is electromagnetic radiation. Then the fraction of the electron energy converted into brimstalling increases with increased electron energy, and its largest power is absorbing materials of high atomic number. The brimstalling energy spectrum is a continuum with photon energies extending as high as the initial electron energy, but low energy photons predominate in number by orders of magnitude in the average energy. So that's how we have actual brimstalling. So know that it's not named after a person. He gave it that name because he noticed that it was stopping for whatever reason. So remember that an electron is negatively charged and the nucleus is positively charged. And there's a force of attraction, so that positive and negative, they want to stick together. And then the strength of this attraction depends on how close that filament electron passes to the nucleus. So if it gets really close to the nucleus, then it can make a difference. The closer the filament electron passes, the stronger the attraction. Then there's more energy and the filament electron loses, and then the stronger is the resulting brims. So what you see right here is, here's your incident, which means this is the one you sent. And so when you got really close right here, well, it knocked one out over here, which is high energy. But this one's a low energy because look where it hit. It's not close to the nucleus. So only the one that got close to the nucleus is what actually sends out the higher energy. So because of this, the brims photon can vary from the maximum kVp that you select to near zero. And this picture is also in your book. And so it's the what you send as to how close it can get to the nucleus. So the higher the energy you start with is the more energy and the closer you're going to get to the nucleus. So when you look at the photon energy, the energy of a brims can be found by subtracting the energy of the filament and how much it leaves the atom with from the energy it had upon entering. So it came in with this and then it left with this, and the average energy is usually about a third of the kVp that's selected. So again, just like our X-rays, when a filament electron hits the target, only 1% of that creates an X-ray. 99% is heat. Well, the energy of the brims photon, this one that gets sent out here, is only about 1/3 of what it started with. And that's a very important thing to know. The energy of a brims photon can be found by subtracting the energy that the filament electron leaves the atom with from the energy it had upon entering. Here's you an example, and I just put it all up there. So it entered with 100. It leaves with 30. So the brims photon now has 70 keV. And that's simple math. So when you see a problem, it says if that same filament passed at some distance from the nucleus and it exited with 80, then the brims photon would only have 20. So it's what it enters, and how do you know that number? That's the number that you selected at the control panel. And then when it leaves, you don't actually know it, but you'll see a problem like this, and you need to know that the brims is left with 70. So what it enters, so if it entered with 100, left with 80, then your brims only has 20. When you think about what it leaves with, that's what actually is going to your patient and then making an X-ray image. So you want more to start with so that you can get at least a third out to make the image that you desire. That's a good way to think of it. In a tungsten target, most of the photons are brims. So that's something you need to know. Most of the photons are brims. One reason is that characteristic interactions, only those that involve the K-shell, have enough energy to be useful. All of the others are too weak to contribute to the radiographic image and are typically filtered out by the beam. And that's what's built into the filtration of the beam. So we'll talk about that in just a second. But because tungsten has a K-shell binding energy of 69.5, only those peak settings of 70 kV or greater can produce characteristic photons. That's something else that you need to know. Characteristic has 70 or more. Anything lower is a beam made up entirely of brims interactions. And that's where that comes in. So tungsten has 69.5, and your characteristic has to have kVp of 70 or more. But the second reason is the filament electron is more likely to miss the orbital because they're in constant motion. and then the atom is almost or mostly empty space. So why are the majority of the target interactions with tungsten targets or brims? Number one, characteristic interactions, only the K shell has enough energy to do something with, and the filament electron is more likely to miss the orbital electrons. So you want it to get close to the nucleus so that it can create a brims interaction. So now that we've talked about characteristic and brims, or brimstalling, now we need to know about the beam itself. So this was the target interaction with the target. Now let's talk about the beam that actually comes out after these interactions. Certain properties characterize any given X-ray beam based on how it was produced and how it behaves in its interactions with matter. Now, the interactions with matter are what we're going to cover in Chapter 7, but you need to know this that I'm about to tell you so that you understand how it interacts. The properties that the radiographer should be familiar with, you guys, is beam quantity, beam quality, and then the defining terms of each. Before we do that, though, we're going to discuss filtration, because your filtration has to do with the quantity and quality is what you start with, but your filtration only leaves you so much to come out. In radiography, filtration refers to the use of a material, usually aluminum. You need to know that. Filtration is usually aluminum, or at least aluminum equivalent, to absorb an X-ray photon from the X-ray beam. This filtration may be in the form of an inherent, added, or compensating filter. So let's talk about filtration. Now, when we talked about in Chapter 1, we talked about the collimator of your X-ray tube, and then the tube itself in Chapter 5. And now that you've been to lab a couple times, you've actually gotten to touch those, and you know what those things do. Filtration is inherent and added to that design. Now, you may have already covered filtration, but maybe not. Inherent filtration is just that. That means it came in the tube head assembly. And so in the tube you already have an inherent filtration of about 0.5 millimeters aluminum equivalent. Now, within that tube head assembly is something called the target window, and that target window is the primary contributor to inherent filtration. So you need to know that, and we have a picture in just a second that shows you that target window. So if you go back and just visualize that tube that we saw the electrons coming and hitting the target, and then it drops down and goes out the window, that's where inherent filtration is. And then in general radiography, the tube head assembly, added filtration is something else. This is another 2 millimeters of aluminum that's placed between the target window and the top of the collimator. So where the window is and then where it comes out the collimator is called added filtration, and the purpose of that, very important for you to know, is to remove low energy X-ray photons from the beam before they can expose the patient and contribute to dose instead of an image. So know that added filtration is used to remove low energy X-ray photons. So in general, all radiography tube and the tube head assemblies have a total of 2.5 millimeters of aluminum. And that is 0.5 that's inherent right here, and then 2 millimeters that's added. And the total filtration is inherent plus added. Now you can have any numbers, and so if you ever see a problem that says, you know, if you have inherent of this amount and added of this amount, know that the total is the total. But this is the typical. So if you were ever asked that, make sure you read the question. In general, it's inherent of 0.5, added of 2.0, and a total of 2.5. And so the combination of all this is what makes it. So here is the tube. So here's the inherent 0.5, and I want you to see this right here. This is the target window. So there's that first bit of aluminum. Now, this 2 added, it says it's between the target window and the collimator. Well, some of it's in the mirror, and then some of it's right here. Now you don't see this. What you will see though, and if you go to lab soon, ask your instructor there if you can see the little slot where you can actually add more right here. And we don't usually do that, but if for some reason our models have something like that, you can add more than that too. But this is what's already in the tube itself. Therefore, the total is 2.5. So the reason this looks like this is because what I said earlier, that added filtration, this is getting rid of all these excess, all that extra radiation, and it cleans it up. So that way, boom, that's all that's coming out is right here, useful, going exactly where you want it to go. Now you can also have a compensating filter, and you need to know that. Compensate means make up for, used to adjust or compensate for variations, and that is the patient's thickness or their density, and you want to create a more uniform exposure to the image receptor. Now the first one is or some type of variation that you can add, but the purpose is right here. So let's just look at this particular image. So here is a foot. Now notice at the toes you do not have as much tissue as you do at this part of the foot. So with this compensating filter, this is called a wedge filter, and see how it's made like this. You can add it, and that way there's more x-rays coming out at the thicker part than there is here. So less photons penetrate the filter and expose the thinner area of the foot. Do we put this on every single image that we take? No, I'm afraid we don't. But you need to know what they are. What is more important is if you think back to something called the anode hill effect, there's always going to be more radiation at one end of the other. And do you remember when I said, remember fat cat? So if you put the thicker portion of the body at the cathode, then that would have more x-rays coming out, okay? So these filters attach. The use of these is the ones that we usually use are, let me see if I have this right here, is this type. This is a boomerang filter, and it's showing you right here. And again, what are we taking an x-ray of? We want to see all of the neck, but you've got chest here, and then you don't have as much right there, and so that type of filter will help filter out some of those other x-rays. Okay, so they can either attach to the collimator or placed adjacent on the anatomic area, and this particular one actually goes under the patient right here, and that's what that's doing. This one's attached to the tube, this one is underneath the patient, but this is the one that you usually use more often. So just know what these are, and the reason we use them, it may give just a little slightly more dose to the patient because you're going to have more exposure to go through those filters, but the quality of your image is so much better. So know what a compensating filter is. Now we want to talk about beam quantity. Quantity, number, you already know that, but it's the total number of X-ray photons in a beam. The radiographer associates quantity with radiation dose. The more x-rays you use, the more dose your patient gets. All other factors remaining constant, an increase in quantity increases the amount of dose delivered to the patient. These are the things that you need to know affect quantity: mass, kVp, distance, and filtration. And we're going to talk about all of those. Quantity is directly proportional to mass. You could have a statement that asks that exact question. Quantity directly proportional or indirectly? Directly means as one goes up, the other goes up. If one goes down, the other goes down. So they go at the same amount. And so you need to know that quantity, if you double the mass, you have doubled the quantity. Doubling mass doubles the quantity of the x-rays that you use, and then when adjustments are desired, mass is the factor adjusted. So that is the normal use of quantity. However, we've said doubled. Now let's look at quantity in kVp. So your KVP is the other factor that you can select. If KVP is doubled, the intensity, which is the quantity, increases by a factor of 4. However, because KVP controls the number and the energy, which we'll learn in just a minute, a smaller change in KV actually makes a larger effect to the exposure to the image receptor. And that's why you have something called the 15% rule. Now, I'm sure you've already heard this, and maybe you've even already done some problems with it. I can tell you, you will have some problems that you'll have to do this. So the 15% rule applies when changing the KVP to affect exposure to the image receptor. A 15% increase in KVP is equivalent to doubling the mass. So if you change your mass, you have to use twice. So that's 100% more. So you're using twice the amount to double the exposure. But only 15% of your KVP does the same thing. And you will eventually learn it's better to increase your KV than your mass so that you don't expose your patient anymore. Okay? Beam quantity is strongly affected by changes in KVP because KVP gives kinetic energy to the filament electrons. That kinetic energy, as we just talked about, is what's needed because the majority of the energy is converted to heat, only a little bit to X-ray. And the greater the kinetic energy, the greater the chances for X-ray production. It's less desirable to use KVP to change quantity because it can influence some other factors, but we also know that there are times when it's better to use it just so you don't radiate too much, because we can use some other things to help filter some of the problems that come with KVP. So just know those two simple rules. Now the other one is distance. Beam quantity is inversely proportional as the square of the distance, and that's the inverse square law. I'm sure you've already heard this particular term. The inverse square law states that the intensity of a beam is inversely proportional to the square of the distance from the source. So here's the actual formula right here. Intensity beginning divided by intensity ending is equal to the end distance squared and the beginning distance squared. And that's hard to put here, but when you see the actual formula, and you're probably going to be working out some of these problems, okay? So you need to know how to do that. So as the quantity quadruples if you half your distance. So if you get closer to from the tube to the patient, you bring it closer, you quadruple the amount of energy that they're getting. And X-ray photons diverge as they travel, and if the distance is shorter, they do not have the opportunity to diverge as much. Therefore, they're concentrated on a smaller area. So sometimes could you change your amount of X-ray that you use? And yes, you could, but the closer you get to your patient, the more likely you are to have a problem with the skin dose rather than the entire dose. Okay, so think about that when you think about your distance. The last one that we have is quantity and filtration. The extent to which the use of filtration decreases X-ray quantity depends on the thickness and the type of filtration material. Filtration absorbs low energy that do not contribute to the image and would actually add to the dose. Added filtration placed at the collimator serves to reduce patient dose. That's what you actually need to remember. Filtration is used to reduce patient dose by removing soft or low energy X-rays. But when you use filtration, it does decrease the quantity, and that amount depends on the thickness and the type, and its purpose is to absorb low energy, and those low energy photons are the ones that create more dose to your patient. Here is a beautiful table that you need to know about, and so you can remember, this is quantity. If you increase every one of these things, increase mass, increase quantity. You also need to know how much, directly proportional. Increase in kV, you increase your quantity. This one's your 15% rule. Increase in distance decreases your quantity. So the further away, the less reaches your patient. Increase in filtration also decreases your quantity. So know these relationships and know that this one is the only one that's directly proportional. This one is inversely proportional, but by the square. This one's 15%. This one depends on the thickness and the other. Okay, our next section is going to be beam quality. Beam quality refers to the penetrating power of the X-ray beam. Your mass and your quantity is going to determine how much of the X-ray actually reaches the patient. Now we want to know how much of it is going to penetrate. Penetration refers to those photons that are transmitted through the body and reach the image receptor. So if you don't have the quantity to reach the patient, they're not even going to get through the body. So you have to think about both of these in together. It is desirable for some of the X-ray photons to penetrate the anatomic area of interest, or you wouldn't get an image. So you have to have it hit the patient, go through the patient, and reach a receptor that's under or behind the patient. Photons that reach the image receptor create the dark shades of the image. So if no photons reach it, those are the light or the clear areas of the image. Both of these create shades of gray, and that's what makes the image and provides contrast. So when I see this picture I threw in here, it's because we're talking about black and white. The X-rays that hit your receptor are going to be shown. This white area means it didn't make it through the patient for whatever reason. Beam quality only have two things that it is affected by, KVP and filtration. Beam quality is mostly affected by KVP. As KVP increases, the beam's ability to penetrate matter also increases. Same way, it's directly proportional. So if you decrease your KVP, so does your quality. So they're both this, goes up, it goes up. If it goes down, it goes down. As KVP increases, X-ray beams with higher energy from high KVP settings, they're considered high-quality beams or hard X-ray, and if they have low KV, they're low-quality beams or soft. And the difference between those is that if KVP increases, then penetration increases, and the high quality or hard beams are what you need to penetrate. Low quality beams, and so that's something else you can think of this way. Hard means I need more kV to get through a harder area. Low quality or soft beams to get through a soft area. Think about bones versus air versus tissue. Now with filtration, beam quality is also affected. We have already talked about the fact that filtration removes lower energy photons, making the energy higher. So think of this, I love this example that I have here in my notes. If an instructor drops a student's two lowest test grades, it increases the student's average. So same with X-rays. If I got rid of those little hang-around X-rays, they're bringing my image quality down. Well, then if I get rid of them, it increases the quality. So if you more filtration increases the quality of your image. Okay. Now here are the two things that affect beam quality. Increase KV increases quality. Increase filtration increases quality. That one's real easy. Now, I can tell you right now, you will probably have some kind of question that says, does mass have anything to do with quality? Always slow down, always read the question. Mass has nothing to do with quality. Now, KVP has quality and quantity. So make sure you remember that when it comes down to any of these values. So, quality measurement. Beam quality is measured by the half value layer, or HVL. Another word for that is its intensity. Got that? Quality measurement is measuring the intensity of the beam. Intensity. Okay. HVL is defined as the thickness of absorbing material that can be your aluminum or aluminum equivalent filtration that is necessary to reduce the energy of the beam to 1/2 of its original intensity. So it says right here to reduce the energy of the beam, but it's how much it takes to go to half. So if you start off with 100% intensity, this half value layer, doesn't matter what it is, breaks it down to intensity of only 50%. The normal half value layer is 3 to 5 millimeters of aluminum. And by the way, Al is aluminum. That's not an I. It's not for artificial intelligence. And you measure this with a radiation detector. So how you do this is you measure the intensity of the beam with that detector, place filters of known thicknesses between the tube and the detector until the intensity reading goes down to 1/2 its original value. So that's a very, very important thing that you would like to remember. Here are some other terms that you need to know about in case you haven't already seen this. Related to the discussion of quantity and quality are the words primary and remnant beam. Primary beam is what is coming out of the tube. Now, yes, nobody's tube comes down this far, but that's just an example. So here's the primary radiation. So you're directing it to this patient's body. Now, I want you to notice if you start counting these squiggles, this is absorbed, it doesn't leave the body. This is scatter, it went off in another direction. So the only thing that comes through is called remnant, which is what comes out or exits the patient. What exits the patient is what actually hits your receptor. Whether it's a piece of film, it's a cassette, it's a CR reader, a direct, a DR, I mean, it doesn't matter. But the remnant beam is what remains after the interaction with the patient and exits to expose the image receptor. The remnant beam can be composed of transmitted, those that we actually sent, and scattered. Scattered radiation is that energy that has lost some of their energy and redirected after interacting. We will talk about more of that in Chapter 7, but just know what primary beam and remnant beam are. Because now we're going into remember I said that we're going to go back to the characteristics and brimstalling? Here we go. There's something called an emission spectrum. We've talked about the definition of X-ray interactions and beam quality, beam quantity. Now let's go back and see how it works. This spectrum, it graphically illustrates the X-ray beam. As previously discussed, the X-ray beam is the result of two different anode-target interactions, and the emission spectrum for each looks different because of the nature. So when you look at characteristic interactions, characteristic photons have a discrete emission spectrum and brims have a continuous. So this is discrete, it's only one line. This is continuous. So the brims just kind of keep on going, and it does this because the energy is changing when it does it. Characteristic has to have a specific. Now, when you look at these, we combine the parts of each to create the emission spectrum, and these graphs are handy visuals of the nature of the beam. So if you ever see this, and we're going to talk about in just a second what this means. Anytime you look at a graph, you have a y-axis and you have an x-axis. So this is the number of x-rays and this is the energy. So a characteristic photon has to have a specific energy. We're at 69 or 70 kV right here. Brims goes from anywhere from 0 to up to 100. So that's the difference in these two. So when we look at a characteristic spectrum, the x-axis is the X-ray energy, the y-axis is the number of photons, and a characteristic interaction is discrete because the photon energies are limited to just a few exact values. Remember, characteristic photons are produced when outer shell electrons fill inner shell vacancies in atoms, and the energy is determined by the difference in the shells involved. And if you go back again, recall all of these photons are named for the shells being filled. So when one leaves and drops into another, then that becomes that, the K, L, M, and on. For example, there's a bar for K characteristic photons produced when L electrons fill K, and then a bar from when the M fills the K, and going on and on. Now, the lowest energy bars may not be labeled because they are of no diagnostic value. So let's look here. These are those exact values that we're talking about. Number of X-rays, boop, and then energy. Well, with characteristic photons, you have a certain amount, but the energy doesn't vary in there. The height of the bars relative to the y-axis indicates the number of photons of that type. This figure demonstrates a spectrum for a tungsten target. Okay, so just pretend like this is tungsten. But the other materials are similar, but the energy range on the x-axis is different. With tungsten, K characteristic X-rays are of the greatest importance because they're the ones that contribute to the image. So we're only interested in these Ks right here because what is tungsten? 69.5. So we need to know that they're right there. Beginning on the right side of the graph, the K photons have a higher energy, approximately 57 to 69. So this is 57 to 69. And then moving down the x-axis, the L characteristic X-ray energies are plotted. So then you come down this way, all the way down to L. And this goes down to from 9 to 12. So this is anywhere from 9 to 12 keV. And beyond L's, there's no point in plotting the energies because they're so low, they're filtered out. So what this tells you is characteristic has exact values. This is the number of X-rays, and this is the energy level. So number of X-rays, and here's your, it could be a range, but these X-rays are not going anywhere else on the spectrum. So if you saw a graph like this, you should just immediately know that is characteristic photons. Bremsstrahlung, on the other hand, have continuous emission spectrum. The x-axis is still the energy and the y is the number. Because brims are the result of the filament's electrons' attraction to the nucleus, the energy is dependent on the strength of this attraction. Their energy can range from just above 0 to the maximum kVp selected on the control panel. Unlike the finite number of characteristic energies, brims have a range. So this is the entire range of a brims. So still the number, but it doesn't get to the number until like the peak, and then it starts to come down, but then you have a range of energy. A graph of brims photons always creates what's called a bell-shaped curve, or a bell-shaped continuum. The left side is just above 0, and the right side is what the kV selected. So this is just above 0, and we probably selected around 90 kV right here. This is a tungsten target spectrum. Other targets are similar, but the energy is different. So just know if you saw that picture, you would know exactly what it is that they were plotting for you. So to graphically represent an X-ray beam as a whole, we combine the two. And with those two spectra, the x-axis represents the energy, the y-axis is the quantity. No different. So the continuous portion is used because it represents most of the beam. Then the discrete line is reduced to the highest energy K characteristic bar. So when you put these two together, and we talked about y-axis is the number, well that's quantity. The x-axis is the energy, so that's quality. And there are 5 factors that change the appearance of this graph and the appearance of how they would be spread out over there. The X-ray emission spectrum is used to graphically represent the energies of the X-ray beam. It can also be used to reflect the effects of different factors on the beam. Changes in the spectrum with respect to the X is quality, changes on the Y are quantity. So let's go and look at all of these. Here's the MA. Now, remember, MA is part of your mass. So we're only going to talk about the MA because we're not going to add the time right now, but it affects the quantity. All other factors remaining constant, if you increase your MA, it increases the amplitude of both the continuous and the discrete portions. Remember, continuous, discrete. Remember, when MA is increased on the control panel, more electrons are boiled off. This increases the quantity. Because the kVp setting controls energy, the spectrum does not move along the x-axis, nor does the discrete line move. So here's what this is trying to tell you. Whether it's a 200 or 400, this is all still the same. But the energy can change depending on your kV. But this is just talking about the amplitude. So a higher amplitude for 400 versus a 200. That's how your graph changes. Now when we go to kVp, changes in kVp affect beam quality and quantity. If everything else remains the same, kVp increases the amplitude of both of them and shifts the right side of the curve to the right along the x-axis. So look where this line is right here. And I'm going to go back one. It's still there, but now we're going with the kVp. So the energy is different, but that's still a finite number for that discrete line. The result is going to be more photons, which increases the amplitude of the spectrum, and which is the higher energy photons, quality, which shifts the right side of the curve farther to the right. And the discrete line does not move because it's related specifically to the target material. If you change filtration, the addition of tube filtration or introducing more efficient filtration removes photons from the beam. Everything remaining constant, an increase in filtration causes a decrease in quantity but an increase in quality. So notice here we added filtration, so it decreases this, but look at it increase the energy level of it. Because it removes more low energy photons than high energy, there's a greater decrease on the left side of the continuous portion, and there's a shift in the peak of the curve. So this is what it looks like when you have aluminum. So remember, when low energy photons are removed, the average energy is higher. And again, the discrete line does not move because it's related specifically to the target material. Then we have the generator. Now, we've not covered generators, but you need to know that for right now, how it does actually affect your quantity and quality. It'll click in together later, but I'm going to go ahead and cover this, and when we get to generators and electricity, you're going to go, oh, Professor McNeil said something about it also affects quality and quantity. So maybe you'll go back and listen to this. Changes in the generator type change the X-ray production efficiency. So it doesn't mean that a better generator has more, it means it's more efficient at producing it. High frequency units are much more efficient in producing X-rays than a single phase. This means that with the same amount of electricity, a high frequency unit produces more, but it means that it also produces more quickly. In the X-ray emission spectrum, this is represented by an increase in amplitude and average. So here we have a couple of different changes in tubes right here, or generators. If a generator operates more efficiently, more filament electrons have the energy to produce X-rays, increasing the quantity. There's also a great number of high energy, increasing the average and shifting the peak to the right. So now this has to do with the different targets, but more so it has that these are changes in the generator also. Okay. The fifth thing that actually affects our X-ray is the target material. So the general radiographer, you do not have the ability to say, hey, I want a different target, unless you're using mammography. Virtually all of the tubes that you have or that you will use have tungsten, but you need to consider how altering the target material might affect the emission spectrum. As the atomic number, or the Z number, increases, so does the average energy and the position of the discrete line on the spectrum. So right here is something that's showing you, here are the different spectrums, right, like this. So the energy increases, but let's just pretend like we could actually use gold. With increases in atomic number, each atom is more complex, having a bigger target. This increases the likelihood of interaction. As quantity increases, the number of energy photons. So the discrete lines represent K characteristic. And there we go. So it says rhodium and molybdenum are usually used in mammography. So these are actually useful things to think about. Gold is never suitable because of its low melting point and high cost, but if you were to use the gold, then it would change the characteristics also. So if you increase your atomic number, so 79, then your energy increases and your quantity increases. So here you go. These lower ones are way down here. Okay. This particular table is probably more important than any of the other things that we've talked about when it comes to the emission spectrum. So if you're looking at that graph where you have the y-axis and the x-axis, if you increase or improve, increase MA, it increases quantity, does not affect quality. If you increase KVP, it increases both. Increase filtration, decreases quantity, increases quality. Increase generator, it increases both, and if you increase your target material, it increases both. So remember this slide and remember the things that go with it. So I think I did a pretty good job of covering all of these. What you need to understand is that before we can talk about the other types of interactions with tissue, you need to know how your X-ray was produced. And so that's what I did today. I talked about all of these different things on the list, and hopefully it's starting to come together and make more sense. Once we get through to Chapter 7, you're going to be much better off understanding radiology physics. And I just throw this picture in there because these are my two little babies, and the little brown one I don't have anymore. She passed away. She had lung cancer, so that was a terrible time for us. But this was when we lived in Colorado. This is Oy, O-Y, and this is Sunny, and they loved the snow. So, and don't think she's trying to bite her. She's grinning because she's happy. They used to just run around in the yard. They have beat this snow down. That was probably started out at about 4 feet before they started running around in it. So, just to give you a happy thing, I don't know if you're still listening or not, but I like throwing that in there. And I look forward to our next ones that we have, okay? So guys, I hope Chapter 6 makes a little more sense to you. I hope you listen to the entire thing, and I can't wait to get started on Chapter 7. Thanks!